Hi, my name is Leah, and I decided to do the suggested class project, so the Chameleon 16 challenge. This is just an overview of my project plan. My first step was to understand the project expectations, then to explore the data. Then the main thing was to create a sliding window function, so I used a zoom level of 4 because I felt like that was enough images, and that was suggested by the professor. I then slid across all the images using the read slide provided function, saving positive and negative examples as JPEGs in my Google Drive. I also saved the indexes of all the slide regions to better reconstruct the mask later, especially for the test images. Then I tried basically 3 different experiments. I tested this whole pipeline on an arbitrarily balanced data set from 4 different .tifs files. I got 250 positive and negative examples from each TIFF. I checked that the sliding window was as I expected, and then I used a pre-trained inception model on ImageNet to basically get my model. Then I compared the above 4 .tifs unbalanced, so I just slid across the entire image and took that as my training set, and I used class weights. Then my last experiment was to include more images and retrain again, and then I compared my results across all techniques and a baseline. And the last thing to do would be to explore more future work and improvements. So during my data exploration, I had some concerns. So one of them is that Inception takes 299 by 299 images. And the thing is, since the .tifs that we have are not divisible by 299, the dimensions, at some point you're going to reach the edge of the image and get a black box like we see here. And this is especially problematic because when you use the tissue mask, it'll consider this black box as tissue since it's black. So my current solution is just to ignore these regions, but a possible future solution would be to encode these black borders as white, and that way it's not considered as tissue. Another concern is that there are these plus signs on some of the slide images. I'm assuming from the slide, the way that it's read at the clinic. And so again, the problem is that these plus signs are black, and so they're considered as tissue. I kind of ignored this issue for this project, but a possible future solution would be to change these plus pixels to white, or to see which images have this issue and just basically crop them. So I made a few design decisions. I used a sliding window of 50 to get overlapping images. Basically, I used 50 because when I wanted to create my balanced data set, I wanted 250 images about from positive and negative class for each .tif. So, and 50 is kind of what got me closest to this number for each image. And then another design decision is that I'm only considering regions of the slide where at least 25% of the pixels are tissue. I just didn't want to overcomplicate anything for the model and just eliminate anything basically because it can't be cancerous if there's no tissue, so might as well exclude them. And then also my data set will be a little less imbalanced. And then I'm only labeling a region of the slide as positive if at least 5% of those tissue pixels are tumor. So then, because I have an overlapping 299 by 299 images, the way I reconstruct the mask is some pixels are going to be predicted as positive more than once because they appear in more than just one image. And so I basically sum up the number of times they're predicted as positive and basically only take the ones that are above a certain threshold as actually being positive, and I take that as my mask. So I wanted to only look at a few test images to compare the different experiments that I ran. I kind of looked through the images by hand and to pick ones that I thought would be good to look at. So I picked this tumor 110 because it has a lot of cancer cells, but then I also wanted a mix of how is it going to perform when there are not a lot of cancer cells. As you can see in tumor 023, you can barely see the mask. Tumor 075 it's more noticeable, but there's also very little. And then tumor 101, which is an interesting slide since it looks like it's almost duplicated, has a decent amount of tumor cells as well. So this is based on my sliding window. I create positive and negative labels basically, and so these are kind of the goal masks of what, if the model predicts perfectly, these are what the masks would look like. I chose a threshold based on the percent overlap that was highest for that image with the true mask, which I can go into in a little bit. But so basically we see that even with the actual perfect data set that I created, even if the model achieves 100% accuracy, the actual mask will not be perfect. And that's because the sliding window, it's obviously squares and the mask is not really rectangular. But for some images, it's pretty good. Like for tumor 101, it's pretty good. Yeah, so then this is the percent overlap from the previous slide. So the percent overlap I calculated based on the pixels that were tissue. I excluded any overlap with pixels that were non-tissue because they're automatically going to be excluded from the images that I generated, and so they'll be automatically predicted as 0, and I feel like that'll just skew the overlap to be really high and not really tell us anything. So yeah, so the percent overlap is pretty good for these, for the perfect case. So getting something close to these values is ideal. And then my baseline is, what if we predict all positive? And we can kind of figure out what the opposite is. So a confusion matrix is not really useful if you predict all negative, or at least the precision and the recall will either be undefined or 0. So that wasn't too interesting. But the percent overlap if you predict all positive is just 1 minus the percent overlap if you predicted all negative. So it kind of gives you the same information. But we see if we predicted all negative for some of these images, especially the last 3, we would actually get pretty good percent overlap to begin with. So that may make evaluating the performance of the model kind of difficult. So these are the 4 images I chose also to create my initial balanced data set. There is one test set that is also in this training set. I just wanted to see if the model was also going to be overfitting or was even capable of memorizing the training data. But I basically picked these 4 images because they each had a decent number of cancerous cells. A lot of the images really don't, so I thought that these were a good medium. So the experiments that I did, like I said, are the first 2 are balanced and imbalanced from the same 4 training images, and then the last one that I called larger imbalanced is 16 .tiff images, also with the sliding window, and just randomly chosen from the set of images that we started out with. We see that the training accuracy steadily goes up, the training loss steadily goes down, but the validation accuracy and loss are very spiky. It's honestly unclear if the model really learns over the epochs. It overfits a lot, so those are issues that need to be addressed if we were continuing with this work. So this is the prediction for the balanced data set. It looks okay. It definitely overpredicts positive. This tumor 023 really barely had any tumor, and that's not what we see here. Again, this is just the percent overlap and a confusion matrix. Then we move on to the imbalanced. It's a little better. It especially looks good for tumor 110. It really looks pretty good. It overpredicts less positive on tumor 023. It doesn't really predict anything on tumor 075, but there's very little tumor in that image. And then in tumor 101, it underpredicts the amount of tumor, but it does manage to actually identify the areas that are cancerous. And again, the percent overlap and a confusion matrix. And then finally, on the larger imbalance, which I had high hopes for since the imbalanced data set between the same images as the balanced performed better, but that's not what we see here. It's very weird looking on 110, very sparse on 101. Honestly, the only one it does better on is 023. But I mean, that's difficult to say because that has such few cancer cells to begin with. The overlap is okay, but it's definitely worse if we look at 110, for example. Here it's 0.81, and here it's only 0.63. So it's a bit strange. So basically, if I were to make suggestions with a clinician about what's going on here, I would say the model is not yet at a place where it can really be reliably used to detect cancerous cells on a slide, but I think it could at least be used to detect areas that are worth giving a second look if maybe the pathologist misses something, because it actually does do, if I were to use this model from the imbalanced data set, it does manage to identify areas, aside from tumor 75, it does manage to identify areas that have some cancerous cells. So it could be used for that as kind of a second, or to identify cases that need a second look from a pathologist, but to actually perfectly identify cancerous cells on a slide, I probably wouldn't really trust this. Overall, though, I think the smaller imbalanced data set performed the best, which is interesting that the larger one didn't. But I think what happened with the larger one is I had issues with slides with those plus signs that I mentioned at the beginning. So I think the data set maybe just has a lot of noise. And I think maybe for a project like this, that kind of handpicking the images to train on just so that you actually have enough to learn from is kind of important, because even with very few images, original images, 4 images at a zoom level of 4, that actually outperformed the other 2 experiments that I did. So areas for future improvement. So again, fixing that concern with the sliding window. So what happens when I reach the edge of the image if I want to include that? To me, it doesn't seem like a huge problem, because a lot of the time the tissue mass is in the middle of the slide and it's not really on the edges. So that also means the cancer is not really on the edges, but we definitely could be missing out on some information from excluding those areas of the slide altogether. And then again, those plus signs or just weird things happening on the slide that aren't tissue but are being identified as tissue. And then I would create probably a larger training set with a focus on images that have lots of cancer cells, like I already mentioned, or change the zoom level to 3, just to have better resolution and more training images. I also would try and train the model from scratch, which I did try to do, but it took a very, very long time to even just go through one epoch, and the results really didn't seem promising even after that. So I kind of just stuck with the pre-trained model, but I would like to explore a model from scratch more. And then choosing a single threshold to create these masks. Right now, the threshold that I used to create these images are the threshold that gave the best overlap for when I kind of got the gold standard mask from the sliding window images that I had. So picking